All right. Where were we? We were conditional jump instructions, I believe, right? Because the last thing we showed, here, am I recording? I am, perfect. Whoop. The last thing I showed, I think, was like this, right? How we know what the hardware looks like to check, okay, 0, was the carry bit high, whatever, and was the significant bit high. That's how it was designed. And again, this is the adder. Really, the value from the adder would go back to like the bus here. I'm only showing it go to the hardware, the logic to check those cases. And remember, we were checking if the value is coming out of like our ALU, which is just that adder. But we're checking if the value is coming out of our ALU are 0, the significant bit is high, or if the carry bit is high. Not if like the value in the A register, no, we're looking at what's coming out of the ALU. And we want to remember if the last operation we cared about had that flag, that signal high. So we had to be careful about when we enable that register. The register will latch in, it will save, okay, what is the status, what are these signals after I'm doing like arithmetic at the right time. Because if we don't do it at the right time, these signals get way out of whack and we're not really observing what we want to observe. Oop. Cool. So, great. How do we start to actually make these instructions? We've got that hardware. How do we make this instructions? Now, again, this is another one of these cases of I don't think it's hard to wrap your head around, but it's definitely not trivial. Okay? It's not complicated, it's not hard, but it's not trivial. So we know that we can do a jump. We have a jump always instruction, right? So we know what the control logic looks like for that. And we also have a way to store those signals based on what the last operation was in a register. So really what we want to do is like based on the contents of the register, if I want to do a jump, if the last operation gave me a 0, like I want to do like a jump if it was a 0. So only when that 0 signal is high, jump is going to work just like jump always. But it's not jump always. It's going to be operand to the program counter, right? That's how we would do the jump. But if the 0 flag is not high, we want our jump when it's 0 to do nothing. We want it to be a no-op, effectively. So only when that flag is high will the instruction do a jump. But how on earth do we do that? Okay, that's what we're going to learn here. But to make sure we got the logic, let's go on. Okay, so the various status flags can now be determined and stored in the flags register. We need conditional jumps. We need the control logic. We need to add this hardware or whatever. The existing control logic that we do have also needs to be updated. One of the key things that we have to update here is like, okay, fine. What do we need to add to the system? We actually have to add that flags register to the system. We need to update our instructions to be able to do like jump 0, jump significant, jump carry. We want those to be there. And we also need to, like how we do that we'll figure out. But we also need to like update our existing control logic for all the other operations. I mean really only for like 2 of the operations, but we have like a new like control signal. If you don't remember, it's that flags register enable. We have a new control signal that is enable the flag register after we've done like addition or subtraction. So it's only on those instructions where we need to have that control signal. But the point is, like, how many control signals did we have before? Like 17 or something? Maybe it was 16. I can't remember. We had 17. The reason I know is we had like 8, 8, and 1. We need another one. So we're going to need to add a new like constant and whatnot. But okay. So there's a couple of things we got to do here to be able to have this working in the system. So conditional jump control logics. The conditional jumps allow the program to jump to different parts of RAM based on some condition, like we were talking about. when the status flag is high. When the respective status flag is high, a corresponding jump would do the jump. If that corresponding status flag is not high, it does nothing. So the program counter is updated to contain the new memory address, the address of the new situation. This is just the way that jump already works. So for example, consider a zero jump command or a jump zero command. Let's call it JMPZ, right? JMPA was jump always. This is JMPZ, jump zero. If the zero status flag is high, update the program counter. If the status flag is low, ignore and carry on. That's a no-op. So this is an interesting instruction because all other instructions were always do this. But this instruction will behave differently depending on the status signal. That's the crux here. So the instruction effectively has two cases, like the jump case or the like the no-op normal default case, let's call it, okay? The control logic for the two version of the instructions effectively already exist. The jump is fetch followed by update the program counter. That's just the jump A instruction. And the do nothing is just the no-op. So we don't have to get overly creative with what the control, like the microcode looks like for those instructions. For the two versions at least. We know what they are. We just need a way to be able to control which of the two versions we're going to do. And there's a lot of ways we could do that, but we're going to go with a familiar, straightforward strategy. So what does not exist is a way to select which version to do, like the jump or the no-op version. So controlling the cases. Do we have any questions actually so far about where we're headed? Controlling the cases. So if a status flag stores the respective condition, they indicate the version of the instruction that should be performed. Okay? Think about it. If we have whatever the instruction is, right? There's 4 bits here. I shouldn't draw them as zeros. Like, I'll put them as like X's, because who cares what they are? It doesn't matter. And then Y is the, right? That's the 8 bits for the, let's say this is like the jump carry, or jump 0, or jump significant. It doesn't really matter, right? So we actually have 2 cases. We have a status signal for, like, let's say this is jump 0. So let's say we have like the JZ, or let's just call it the Z flag. Right? That's what I called it there, I think. That's a bit. It's a status signal. If it's 0, like think, every other instruction, jump always acts the same way. Add always acts the same way. But we have jump carry, or jump 0, or jump significant. If this is the 0 flag, if the 0 flag is low, this instruction should be a no-op. But if it's high, it's going to be another one. So this flag right here basically gives us like a branch. Right? Now, have we ever seen any design where like, oh, well, okay, how can we kind of modify something like a lookup table and add another bit that has like a different meaning, but it basically selects 2 different chunks of the lookup table to run? Remember doing this like several times, like what we already did with the lookup table for the control logic with the microcode counter, and what we did for the sign signal for the output register? That's exactly what we're going to do here. We're just going to add to the lookup table. In fact, we're going to do that 3 times for the, I don't know if this is the order I do, but we're going to do that 3 times for the lookup table. Now, when you look at this, that means the lookup table is going to get a lot bigger because you got to double it again, double it again. In fact, it's going to be 8 times bigger than it was before because we need to have the control logic for every combination of those 3 bits. So the lookup table is going to get a lot bigger, and there's going to be a lot of redundant information because imagine we have like load A from RAM, right? What is the control logic for load A to RAM? Well, this is already in the lookup table. Well, if this flag is 0, what is the control logic? Well, it's one way. If this is 1, what's the control logic? It's the exact same way. It doesn't change. So we're going to have a lot of redundant repeated information, but that's fine. It's a lookup table, easy peasy. Anyways, I'm jumping ahead. We're gonna get right there. So, okay, the status flag, okay, the same idea used for dealing with the output register signed, unsigned case can be used here. Multiple lookup tables with the multiplexer could be used, or a single larger lookup table where one of the bits in the input pattern for the lookup table kind of controls which chunk of the lookup table to look at. This chunk corresponds to when the Z flag is low, this chunk corresponds to when the Z flag is high, and so on. Here we go. So with the idea, this is what we got. We have our operator, we have our count for the microcodes. Here, don't get it. This was me saying the instruction, the operator operand. Here, this is operator microcode count. It's just a bad coincidence that I used X and Y. And these are the various flags. Point is, our lookup table, which originally had 6 inputs, will have 9. 6, the 4 plus 2, and then 3 more on what do I do for each instruction based on the various stages of this. Cool? Cool. So like before, different segments of the input to the lookup table, different segments of the input to the lookup table have different meaning, right? The least significant 2 bits, microcode counter. The middle 4 bits, that's the operator of the instruction. And the new 3 bits are the various status flags. So something like this. This would be like an example of the lookup table. Okay? Now, what do we have here? Okay, so this is our microcode counter. This is some instruction, right? So imagine we have some arbitrary instruction, doesn't matter so much what it is. We got it there. And then we have the various flags. This is our new control logic lookup table. It's got 9 inputs, 0 through 8. The least significant 2 are the microcode counter. The middle 4, that's the instruction operator. And these 3 here, those are the control logic. You'll also notice down here we also have a FLG. That's the flag register enable signal. So I also added the new, I have 0 through 17 here, so there's 18 control bits, control signals here. Because this one here would have to go to that flag register to when and when not to enable it. So right now we're working on like, okay, we have to update the control logic. We updated the hardware for the control logic. We've got more inputs, got ability to input these values, the signals, and we have the ability to output additional control signal there. That's where we are. But we haven't looked at what the lookup table's content looks like yet. We'll get right there. But do you have any questions about this general design? No? Everyone's happy? Cool. So since they're the additional inputs, the size of the table's inputs must grow. Each segment, yes. So keep in mind though, like when these are all 0, we still have like 16 instructions, right? Plus, for each instruction has 4 parts to it. But there's still 16 instructions. But then when this is high, we have like, well, what do the 16 instructions look like when this is high? What about when this is high? What about when this is high? What about if these 2 are high, or these 2, or these 2, or all 3, you know, and so the various cases. So we end up having 8 batches of the 16 instructions. Almost all of those batches are going to be identical. The only difference will be how do the respective jumps work. Each of the 8 segments of the lookup table, since there are in addition, the size of the lookup table grows by 8 times. Yeah. Each of the 8 segments of the lookup table correspond to how the instruction should work given the state of the status flags. The state of the status flags, huh? However, of the 16 instructions, only the 3 conditional jumps will be different depending on the status flag. So with this design, yeah, we have a lot of redundant information. Is it clear that we have redundant information? Because like addition or load A or output is going to be the same regardless of what the status flags are. It's only the 3 jumps that we're going to add. All right, with this design in mind, there still needs to be control over when the status flag is enabled. That's what that control line is there. That's why we have another control signal that we've added to our system. Okay, enabling the flag register. So the status flag register needs to be enabled at specific times. Only enable it when performing addition or subtraction. I don't want it to be enabled at any other point in time. In fact, it's not even that I want it enabled during addition and subtraction. I want it enabled at a very specific time during addition and subtraction, right? So it's another microcode, and we have to put that microcode in the right spot, or a modification to the microcode. So every instruction is allocated 4 clock cycles, although addition and subtraction only require 3. Fetch 2, output from ALU to the A register, and set the subtract signal when necessary. Okay, therefore the question is, when exactly should the status flag signal be set high? Okay, right? So addition and subtraction. When should the status flag signal be set high? Like if we go here, let me go here real quick. Right, we're going to see this. Can you see this reasonably well? The glare in here, it's really bright, right? So it's kind of hard to see. So here's addition and here's subtraction, right? So each instruction does have 4 steps that it could have, 1, 2, 3, 4, based on the microcode counter. Unless you're thinking about what you did in the assignment, right, where you end early. Raise your hand if you've done the assignment. Okay. Okay, cool. So, yeah, the end early thing, right? You can think to that, because that's what we're getting at here. When should we enable the flag register enable? Okay. First and foremost, we could talk about it, but first and foremost, not during fetch, that's for sure. Should we, would it even make sense to do it there? Maybe, I don't know. I suppose, like, maybe you could say here or something. Long story short, you want all your fetches to be the same. Never mess with fetch. Leave fetch alone. Never mess with fetch. Okay? So the question is, should I put it here? Should I put it here? Should I put it here? There? Like, I got some questions. Could we put the enable here? No. That would be a problem. Why? Because I'm outputting from the ALU into the A register. The value in the A register would change. What the ALU kind of like has ready for output would change. Therefore, the status signals would be completely irrelevant to the last operation. It wouldn't work. This is kind of what we were getting at last time. Because think, remember with addition, if I had like 5 and minus 5, let's say it's subtraction. 5 and minus 5, so subtraction here. Before this goes, that adder is already like ready to output 0, right? Before we do any of this, it's ready to output 0. After it does this microcode step, the value in the A register goes from 5 to the result, which is 0. So the value in the A register becomes 0. And now our adder has 0 minus 5, negative 5, ready to be output. But we're not going to output from that adder anymore, right? We've got that driver that blocks the output. Because remember, the adder, no matter what, is always calculating the result of the A and B register. It's just when we output from that to the bus, that's like when we had control over it. So the point is, I can't do it here because if I did, A changes, meaning what's in the adder changes to something that had nothing to do, I mean, it had to do with the previous operation, it's related to it, but it's not the result of the previous operation. So, quite clearly, we can't put it here. But, can we put it here? Is it safe to put it here? Here's why I'm asking, is it actually, let me make sure I don't have it explained in the content here. Okay, therefore the question is, where exactly should we do it? It does not make sense to do it during the 2 clock cycles of fetch. They got to be the same. Leave them alone. It has nothing to do with the underlying instruction, okay? It could work during the ALU. At this instant, it could work during the ALU to A register step. At this instant, the value in the ALU has the value to be calculated, right? So the value coming out of the ALU, I want it to be, like, that's the value I'm calculating. So if it was like a 0, the 0 flag should be high. I want to latch it then. Okay? This means the status flag have changed, for example. Okay, therefore the status flags at the time relevant. Okay, this is just me saying what I already said. Therefore, the flag register enable should be high at the time that the ALU is being output. Okay. Let me, digital. Perfect, right? So, run. If I've got perfect. Okay. So here I'm doing like 5 minus 5. This would be like a microcode step, right? I'm about to output from here back to the A register, which, you know, this is the stand-in for whatever's in the A register, right? So this is what I want to go back to there. But we can see at that instant, that's when we want the 0. Yes, it's 0. That's when we want to latch it. Yes. Perfect. But is it possible, like, let's go back to our, is it possible that, like, this is a big concern. We've talked about this before, and you may have thought of this during the assignment if you worked on this part of the assignment. Is it possible that the value from the adder, it's being sent to the A register, right? So the value in the adder is being sent to the A register, and I want this to be sent to the flags register, right? Is it possible that the system latches data into the A register, thereby modifying what this is in the output of this, before that status flag can latch into the flags register? My question really comes down to how synchronized is my system? I want to be able to latch into the A register and latch into the flag register at the exact same time. I suppose it's fine if I latch the value into the flag register before the value gets latched into the A register, right? Because I can latch into the flag register fine. Oh, then the Z, then A updates fine, but I already latched the Z flag. Okay? That's fine. But if it was possible that the A register's value latches in before the flag register's value, we'd have a problem, right? We would effectively have what I've been stressing. So, how synchronized is our system? And this is a big question. This right here is a question we need to be very concerned about. Us in this class with our system, we don't really need to be that concerned, but it's something to be aware of, because when it comes to designs of system like this, these are some of the limitations we have. How synchronized can our system really be? If the synchronization gets out of whack just enough, and this becomes a bit of a problem, imagine we think these things are being latched at the same time, but they're not, and we think we're latching the result of the A and B we want, but really we're latching the result of the A, B, back to A, updated, and then latched. That would be a big problem. So is it possible? For us, realistically, it's not possible. It's designed such that these things are designed such that when the clock happens, the value is like sitting here, like, imagine like this is my register, and I'm like right here. Okay, the value is right here at the register. This is the Z flag. And then over here is like, I'm trying to latch in, let's say right here, I'm trying to latch into the A register. Like, the data is right there already. The signal on that line is right there. It can't go into the register until there's a clock cycle. That clock cycle is like, okay, go. So the data is already there. It's not like there's like this like travel time. There is, but like consider that the data is already there. So the data is there, and the same data is right here. So when it happens, and the clock is happening such that it happens at the instant of the clock cycle, they're both fine. But it is reasonable to wonder, how synchronized is my system? If these things aren't synchronized, am I in trouble? If you really wanted to hedge against this, what you could do is say, okay, at this moment, before I ALU out, at this moment, the value that the ALU has is the value I want to like observe for the status signals. So I could latch into the flag register before any of this happens. The only way I can do that is to move these two to here, the fourth step, and then give latching the flag register its own microcode step. And then we would be super safe. Latch the status signals, then output. And then it has a chance to modify. Because it's entirely fine to latch the status flags, then A. It's fine to do them at the same time, but it is not okay to latch A and then the status flags. So we could design it that way. However, for us, it's not going to be an issue. And there is a cost to that. You can say, what's the harm in being more safe? The harm is it uses an additional clock cycle. You might say, but it takes 4 clock cycles no matter what here anyways. Yes, but that was our design, and if you do the assignment, you will see how you can modify these to be a little faster, which is nice. So I've said this a bunch, and I'm going to keep saying it. There's always a trade-off. Just like there's always a trade-off in the software you design, there's this trade-off in the hardware. And it's interesting to think about that. Is that all clear? Cool. All right. So one may wonder, is it possible for the value from the ALU to be latched into A, thereby altering the status signal before the value from the status signal can be latched into the flags register? This is not an unreasonable question to ask. It can be addressed by making an additional and subtraction take 4 clock cycles, right? Yeah, we just said that. However, this is not a real concern given the synchronization of the system. Within digital, values are latched into registers the instant the clock goes high. In practice, there would be some delays due to physical limitations of the hardware, but the delay on latching a value into a register would be less than the... This is also suggesting that like the time it would take to go from the ALU to the flag register versus the time it would take to go from the ALU to the flag register, no. ALU to flag register would somehow take longer than, let me draw the components. Here's why like this concern is perhaps, there's an argument that it's unrealistic that this is a concern. Because ALU to flag, there is a time there. And then ALU to A, right, there's a time there. So, is it possible that the time it takes to go from here to here is somehow longer than the time it would take to go from the ALU to A back to the ALU to the flag register? Probably not. That's ridiculous, right? Why is it so ridiculous? Well, we'd have to, first of all, it's clearly a greater distance, but also, how could a second signal beat the first signal here, right? Like it has to go that same pathway. So obviously that's kind of perhaps a little overkill, but it's still a really interesting point of discussion nevertheless. All right. All right, including the flag register in the system. Okay, we talked about how we have to like update the control logic, at least for adding and subtracting those instructions. So like the contents of the lookup table for those corresponding instructions need to be modified. But okay, that's great and all. But how do we actually add this flag register to the system? Well, here's how I did it. I put it right here. Okay? So what do we have? I took, look, here's the adder. The adder still, through the driver, goes back to the bus. But we've got this signal right here, and also the carry signal right here. They go over here. And if you recognize this from what we just did, this checks 0, this checks the high bit, and this is the carry. All right? Flag register. Yeah? Then from the flag register, the output of the flag register, which is those 3 bits, right? It's on a single signal, goes down here, gets split into the 3 that go into that lookup table. So this lookup table has those 9 inputs. And finally, we have, okay, obviously it's connected to the clock, but we have this enable signal that comes in, well, it's one of these new control lines right here. Pretty cool, right? Now all the gaps on the ESAP system are filled in, eh? No more gaps. It's nice and complete. Cool, right? Yeah. You better enjoy this. The amount of time I put, like you might be like, how long did it take to move it? It's not just moving it. Every time I move something, I have to go and update the digital files. I have to go and update the figures. I screenshot, output, save, resize, update. Maybe sometimes it requires updating the course. Making one damn change to any of these placements here was such a nightmare. And 9 times out of 10, I would take like a screenshot where I had the grid on, and then I'd upload it and then be like, and then I have to do the whole thing over again. So what I'm saying is you better appreciate this. This is a nice design. I put a lot of work into it. All right, cool. Again, where these signals here from the adder are basically, well, we're observing the carry out. It's not doing anything else. We're observing the data coming out of the ALU. 0 significant carry. Flag register. The output of the flag register is always being fed into this lookup table for the control signals. Again, microcode counter, instruction operator, control flags. And we have a control line coming into here to control when this flag register is enabled. We already talked about all those bits. All we did now was combine it to our system, our bigger system. All right. Any questions? If you do, ask them now. To be clear, if your question is, but how does it know? It doesn't yet. We need to go and screw with this. We need to actually fix this lookup table's contents. And again, thank goodness it's a lookup table and not a gigantic mess of programmable logic array of ands and ors, because that's just, I don't want to do that, right? So we're going to, a lookup table, easy peasy, cool. Any questions, thoughts, concerns, comments, anything at all? All right, let's fix the lookup table content. So the content of the lookup table needs to still be updated to account for this new stuff we want, right? The 3 new commands, instructions, for the 3 different conditional jumps need to be implemented. The status signals serving as inputs to the lookup table need to be accounted for, right? We've got additional input lines. And we need the additional output signal from the lookup table to control the flag enable. So a modified version of a script that we already used. We wrote that script to nicely generate, like which script? This script, to nicely generate, oh, this is the updated version. Oh, this whole time I was using the updated version, you can see that I added the flag there. All right, well, I thought I was using the old one. It's fine. We can update the script that we already wrote. That's why this looks pretty damn familiar to you, right? Okay. First thing we do, add a new control signal, right? A new bit pattern for that control signal. And I put it right here. And you say, why there? Why not at the end? Why? So it would fit my pretty design. That's why it's where I put it. There's no other reason. And again, you look at this and you're like, that bit pattern means whatever 2 to the power of 8, 16, 15, 4, 2 to the power of whatever that is, right? Remember, it's not about the integer value here, it's about the bit patterns. The bit patterns are what we want these to really be. I know that that's an integer, but I just care that it's a bit pattern. How do I know that there's also 18 here? Well, these are groups of 8. These underscores don't need to be there. I don't know if you know this, but in Python, if you want to to add visual clarity to your numbers, you can add underscores. It has no impact on the value of the number. It's just a typographical thing, right? So if you've got if you groups of 3, it's handy if you've got millions or billions and you're looking at a number, you're like, what number is that? It helps, right, for visual clarity. Here I did it in groups of 8 because bits, bytes, makes sense. So 8, 16, 17, 18, that's right. So I did have to update the halt. I did have to update these ones, obviously, to insert the flag register here. And then everyone below, I didn't really need to add an extra the zeros here because there's assumed leading zeros, but for consistency and intentionality, I included the leading zeros. Right? Right? Cool. Yeah? Yeah. Any questions about these constants? Remember, it's just the bit patterns, right? And they're just there to make it easy to be like, which signal do I want to go out from this lookup table? Now, because, I'm going to also create 4 new constants, one for each of the jump instructions. Jump always isn't that special, right? But it's very similar to the others. I'm just going to set these here, these constants. These are the bit patterns for those respective instructions. You can see that I put them in the blank spots. These were no ops before. They're still no ops half the time, right? But anyways, I just kind of group them together. Makes sense. I'm just setting them aside because it'll make some, you'll see what I do with the code. The microcode instructions are stored in lists. The specific microcodes for each instruction will be created with bitwise ORs. The difference here versus before is that we've included the flag signal here, right? There. So this is exactly the same as before, except for I added the flag enables here. We ORed it with these constants. All right? Now, also these 3, I've also added the instructions for jump 0, jump significant, jump carry here, obviously. But this would be like the default way they work. When all the status signals are 0, those jumps should do nothing. They should be no ops. So I leave them alone. Right? Yeah? So far, so good? Okay, so how are we going to add these things? Now, there are a lot of ways we can add these things. Maybe the way I added them, the way I programmatically included them in Python here to generate the lookup table, I will admit that I wrote it in a way to amuse myself and impress myself with how good I am with low bits and whatnot. So it may actually hurt how well you can understand it. I don't think it's too difficult to understand. But I do admit that most of it, I was just kind of impressing myself with how I did it. So if you're like, why would you do it that way? Because I wanted to. If you think it's unclear and you would have done it a different way, more power to you. It's entirely fine. How many ways are there to solve a problem? An infinite, right? So here's the 16 instructions. However, the conditional jumps need to work differently in the various cases. That's what this is all about. So by just saying, oh, they're 0, well, yeah, they're 0, but that's their default behavior. We need to somehow account for these things. So, and also you'll see that, okay, here's what the 16 instructions should look like when the 3 status signals are 0. Here's what I'm going to do. I have to repeat this 8 times, right? 1 for each of the various all possible combinations of the 3 bit patterns. If you're like, why 8? 2 to the power of 3, right? How many combinations of 3 bits are there? 8. Anyways, so all I'm going to do is I'm going to take this, copy, paste, 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 paste 8 times. But for each time, I'm going to just update this, or this, or this, depending on where I am in that bit pattern. I'm going to update that no-op to not be a no-op, or the jump to not be a no-op, but to be But jump always, basically. That's what I'm going to do. Okay? That's the idea. All right. Actually, I've got a pretty, I think my comment in here for how I explain how I do it is pretty nice. But I'm going to see how I explained it here, and then if I don't like it, I'm going to go through my comment. So what do I have here? Okay, the above, however, the conditional jumps need to work differently. As discussed, each row individual microcode is accessed by some input pattern in the lookup table. With this new design, the three most significant bits correspond to the status signals, right? The C, Z, and C, S, and Z carry significant 0. Flags, instruction steps. The above list of 16 instructions in microcode corresponds to the first set. So there'd be like 0, 0, 0. We have those 16 we just saw. If I say 0, 0, 1, I have the 16 we just saw, but this one should have this there, right? If it was 0, 1, 0, this would be there. If it was 1, 0, 0, that should be there. If it was 1, 1, 1, this should be here, here, and here, right? Right? Because it's possible, remember, like, all the status signals can be high, but I don't give a shit, right? But like, each jump would still work if it was, right? All right. All right, so the 16 patterns would follow like this particular like system. And if this pattern doesn't make sense to you, good luck. When the flags are 0, 0, 0, then no flags are set. 0, 0, 1, 0 flag, 0, 1, 0, sign, significant flag. 0, 1, 1, that's a significant, and the 0 flag were high. 1, 0, 0, carry is high. 1, 0, 1, carry and 0 high. Uh-oh, I messed up. Typo, typo, typo. That should say 1, 1, 0, carry and significant, and then 1, 1, 1, all of them are high. So I need to update those 3 jumps for when they're to be like the jump always when their corresponding bit is high. That's it. That's all I got to do. All right, so for each of the 8 groupings, the conditional jumps will act as a jump when the respective status signal is high. Otherwise, it acts as a no-op. So how do I do it? Here's how I did it. This was like what I mean by like, I thought this was a pretty cool implementation. I liked it. If you hate this, deal with it. So how am I doing it? Well, I'm running to the hex file. No matter what, I start with v 2.0 raw, whatever. And then, okay, for the status, for the flag state in range 8. Okay, this is a loop that's going to go from 0 to 7. Okay? 0 to 7. We're looping for each of these bit patterns, except this one would be correct. Okay? So for each grouping, I'm calling it the flag state, for I instruction and enumerate instruction, so loop over each instruction. Now, if I is equal to jump Z, meaning that the current instruction I want to do is equal to jump Z, right? Which would be this one. And if you're like, how does it know it's that one? Because of that constant, right? If it's that number, what number is that? That's 8, 9, 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it's the jump Z instruction that I'm to be writing, should it be a no-op or should it be a jump? Right? That's the question. So, if it's the jump Z in the status flag and 0, 0, 1, basically by taking the status flag count, is it 0, 1, 2, 3, 4, 5, 6, 7, 8, ending it with 1, if the result is not 0, that bit was high. That's what that means, right? Okay? If you're like, wait, what? You can figure that out. All right? So basically, if it's 1, right? Look. Because I'm seeing blank faces. If I had 0, 0, 0, 0, 0, 1, and I ANDed those together, what do I get? What's 0 and 0? 0 and 0. 0 and 1. Right? There you go. If I have 0, 0, 1 and 0, oh, I get 0, 0, oh, I get 1. Oh, and hey, that's the Z. That's hey, that's what I want, right? If I have, here, let's just, 1, 1, 0. What's 1 and 0? 1 and 0. 0 and 1. You get it now, right? Basically, when it's not 0, hey, that's what we want. And then I say, okay, or if it's the significant one, and I do it with that bit, or it's the jump carry, and it's that bit. Basically, if I found a case where the instruction should be the jump, I just put in the jump instruction. Okay? And wait, how is JMPA the index of the instruction list? Because that's a 9, and that list at index 9 is the microcode list for that particular jump. All right? Otherwise, just write the whole thing. Just leave it alone. Take the current instruction and put it into that line. Cool. Cool? I think that's cool. You can see what I mean, right? This is pretty cool coding, right? Isn't it fun? I think it's always kind of fun to program with like bits in mind, right? Doing like actual like bitwise Boolean operations. I think that's so fun. Yeah. All right, already there. And now, yeah, cool, right? Come on, you should be so impressed. All right, and then finally, we would load this into our lookup table, and that's it. With that new thing, our system is now Turing complete. We have a complete computational system. Clap. Yes, clap for me. Yes. There you go. There we go. We did it. Obviously, its biggest constraint is we have 16 bytes of RAM. That's a big constraint. But we can do everything computationally. If we go back to that problem we had of, all right, print out a 1, if some value is less than 10, otherwise output 0. Remember we talked about this like 1 or 2 topics ago, and it was like, oh, curses, we can't do it. Can we do it now? Yeah. We now have the ability to make a decision. So how do we do it? Load a value into register A, subtract 10 from the value. If the result is negative, the most significant bit is high, the value must be less than 1. If the result is negative, jump to the part of RAM that outputs a 1. How do we jump to the part of RAM? With the new instruction, JMPC, which I think was JMPS, which was 11, right? So the bit pattern 1011. That's our new instruction. Or B, right? B, no, A, yeah, B, yeah. If the result is not negative, output 0. So what would the machine code look like? This is what the machine code would look like. Here I put the number 5, because why not, right? But what do we have? Load into A the value from F. What do I have? I've just got 5. It's some example value. It doesn't really matter. I load into D, in B direct, the value A, 10. 8, that's subtract. B, that's jump. Jump where? Jump to memory address 6 if the result produced, if the significant bit was high. Otherwise, we do nothing. So if it is high, we jump to 6. 0, 1, 2, 3, 4, 5, 6. What do? That's output the contents of E. The contents of E is a 1. F, halt. But if we didn't jump and we just did a no-op, we just carry on. Output the contents D. That's a 0. Halt. Now we actually can jump. This will actually work. We're out of time. I guess I'll have to wait till next week to see it run. If you can't wait, you can run it on your own. All right, I'll see y'all later.